In everyday language, we use words like constant, variable, hypothesis, and sampling loosely, and that creates confusion in decisions. Today, we will translate those terms into a practical way of thinking that supports clear analysis. We will focus on interpretation and decision relevance, using simple examples to anchor the ideas. Most people recognize these terms, but may not recognize the boundaries between them. In statistics and research, small definition shifts change what you can responsibly claim from data. The goal is not to sound technical, but to make sure your conclusions match what you actually measured. When definitions are clear, teams argue less about labels and more about what decisions the evidence supports. A constant is a fixed numerical value that shows up in an observation or relationship. A parameter is also a constant, but it sets the specific version of a broader equation, often written as small letters or Greek symbols. A variable is what changes across cases and is commonly written as a capital letter. In business terms, variables are what you measure across items, people, or time, while parameters or constants describe the rule you believe links them. In the total costs equation, A is a parameter, 1.20 is a constant, whereas TC, VC, and FC are variables. When two variables relate, one is typically treated as dependent and the other as independent. The dependent variable is the outcome you want to understand, often called Y. And independent variables are the factors you believe influence it, often called X. People often get stuck on the terminology instead of the concept: what changes, what responds, and what you are trying to explain. If you mislabel X and Y, you can still compute results, but you will get the wrong story from the data. And the wrong story can derail your decisions. Imagine you are studying how high a hot air balloon rises. The height is the variable of interest, meaning it is the dependent variable. Internal factors like balloon material, balloon size, basket weight, and hot air temperature can all affect that height. External factors like humidity, outside temperature, wind, and launch location can also matter, even if they are harder to control. The goal is what matters. Identify what affects the rise of a hot air balloon and how. Research methodology hinges on correctly identifying dependent and independent variables, then controlling what you can. This allows one to study the effect of each independent variable on the dependent variable. In the balloon example, you try to hold other factors steady, while you change one factor at a time to see how height responds. What happens if you reduce the weight of the basket, leaving everything else the same? Does the time of the day impact the height the balloon can reach? Some variables like the internal factors are controllable, while external variables remain uncontrollable, even though they vary. This matters for business decisions because it clarifies what you can actually influence versus what you can only monitor and plan around. Consider the relationship between a child's height at age 2, x, and expected adult height, y, represented as y equals 2x. Here, x and y are variables because different individuals have different values. The 2 is a constant that defines the relationship in this example. Interpreting it is straightforward. Once x is known, y follows from the stated rule, and adult height is treated as the dependent outcome. In the real world, relationships are not always so clearly defined. However, starting with simple formulations helps you understand the rule before accounting for real-world variation. Real work often looks less certain than y equals 2x. So we may write a more general form, y equals a plus bx. Here a and b are unknown parameters that give definition to how y relates to x. Using measurements and statistical tools such as regression analysis, you should estimate a and b from data, rather than assuming their values. The business meaning is that the linear relationship is not taken on faith. It is shaped by observed evidence, with the estimate summarizing how strong the connection actually is. The equation y equals a plus bx represents the entire set of possible straight lines in an xy plane. The intercept a and slope b are parameters because each line has its own fixed values for them. For example, y equals 5 plus 2x differs from y equals 10 minus 2x because the parameters change, even though both represent straight lines. For decision-making, this helps you separate the stable form of your model from the specific parameter values you need to learn for your context. As we discussed earlier, these parameters can be estimated from data. We can also extract information on how reliable our estimates of these parameters are, to ensure that we are making the right decisions based on the correct relationships. A word of caution: if you misrepresent y and x, the parameter estimates will change, and that will affect your decision-making. When teams agree on definitions, they reduce confusion and strengthen decision alignment. Start by naming the dependent variable clearly. Then, list independent variables and distinguish which ones you can control. Use simple relationships to communicate meaning: what stays fixed, what varies, and what must be estimated from data. Revisit one current business question and see if you can explicitly identify the y, the x's, any constants, and possible parameters before you even touch data sources.